Let's look at an example here. We're going to show that 5 is an eigenvalue of this matrix A, and we're going to determine all the corresponding eigenvectors. So our goals for this example, first of all, we want to show that ax equals 5x has a non-zero solution. That's what it means for 5 to be an eigenvalue of A. And secondly, we want to find all non-zero solutions themselves. These non-zero solutions are the eigenvectors of A corresponding to the eigenvalue 5. Let's start with 1. Well, the equation 1, this equation over here, is the same. This is the same if we move everything to one side as saying ax minus 5x equals 0. We can then factor out an x to get A minus 5 times the identity matrix, if you want to be specific, the 2 by 2 identity matrix, times x equals 0. Note that we cannot just write A minus 5 because you can't take a matrix and subtract a scalar. So let's see, what is A minus 5I2? Well, A minus 5I2 is equal to minus 4 to 4 minus 2. And we notice that the columns of this guy are linearly dependent. So by Tim, A minus 5I2, the system A minus 5I2 times x equals 0 has infinitely many solutions. In particular, it has a non-zero solution. Therefore, 5 is an eigenvalue of A. So now let's go and figure out what are all the eigenvectors. Well, what we need to do is we need to look at the system of equations with augmented matrix, this guy. Well, this augmented matrix is just minus 4, 2, 4, minus 2, the zeros here, and we can row reduce, so using Gaussian elimination, to 1 minus 1/2, 0, 0, 0, 0. And therefore, the solutions the solution set is the set of all guys t over 2 t such that this colon means such that t is in R. This is called set builder notation. Therefore, the eigenvectors for A, which correspond to 5, are all of these guys which are not 0. So they are the non-zero multiples of 1/2, 1. This brings us to the following definition. Let A be an n by n matrix, lambda an eigenvalue of A. The set of all eigenvectors corresponding to lambda, together with the zero vector, is called the eigenspace of lambda, denoted E lambda. In other words, E lambda is the null space of A minus lambda I. In particular, E lambda is a subspace of Rn. In the above example, which I have helpfully removed from the screen, E sub 5 is equal to the span of the vector 1/2, 1, which is what we found. Let's look at some more examples. Take a look at this matrix A equals 2, 0, 0, 2. I'm going to give you a moment to try and see if you can come up with an eigenvalue of this matrix just by looking at it. To kind of give an idea, well, what does it do to the vector x, y? Well, A times xy is equal to 2x, 2y. And this is true for any x and any y. But that's the same as 2 times xy. It's 2 times our original vector. So therefore, 2 is an eigenvalue of A, and its eigenspace, E2, is equal to all of R2, because this works for any x and any y.